Hello everyone, I'm James and welcome to episode 13 of the OpenGL tutorial series. Today we're adding fancy effects to the water. The first thing we'll start is with the Fresnel effect. So the Fresnel effect, as I explained before, is when you look from the top down into the water looks transparent, but when you look at a shallow angle, the water looks reflective. Then we'll add some distortions and finally some specular lighting using normal mapping. Let's go ahead and begin.
If we have the camera at this angle, we want the water to be fairly transparent. If we have the camera at a more shallow angle, we want the water to look more reflective. These are the surface normals at different positions on the water. We'll later distort these normals when we add specular reflections. These are the vectors from the surface of the water pointing towards the camera. Let's put the camera at a higher place. Take note of the relation between the surface normal and the vector to the camera. Now the vectors pointing towards the camera are more similar to the surface normals. How do we get the similarity of the vectors as a scalar value? We can once again use the dot product. And that, my friends, is how we'll get the Fresnel effect. We'll start by adding the camera's position as a parameter in the entity's render method. Next, we'll send the camera's position as a uniform. In the water vertex shader, we'll take in the world matrix uniform. We need this matrix because we need the world position. We'll send the world position out as a varying variable. Calculating the world position is very easy. We just need to multiply the world matrix with the vertex position. In the water fragment shader, we'll take in the world position varying variable. We'll also add a uniform for the camera position. In the main function, we'll define the surface normal, which for now will be hard-coded to an up vector. Getting the vector pointing towards the camera is very simple. All we have to do is subtract the camera position from the world position. We'll also normalize the result. Finally, we'll calculate the refractive factor with the dot product and use this factor as the last parameter of the mix function.
Let us fix the errors in the scene source file. All we have to do is add the camera's position. So camera.transformation.position. And we'll do the same thing for the skybox. And we'll get the main camera transformation and position for the water, which is the most important one. Now if we run, there you go, it's working, look at that. When we look from the top it looks very transparent. However, if we look from a shallow angle, you can see that it's way more reflective. Awesome. Let's add fancy distortions now.
It's actually really easy to add distortions to the water. All we need is a DU/DV map, such as this one. A DU/DV map, as you can see, is made from red and green pixels. The red channel specifies the offset in the x-axis, and the green specifies the offset in the z-axis in our case. So all we have to do is load the map in our shader. We then sample it, and then we'll distort the reflection and refraction text chords appropriately. Let us begin by adding a texture for the DU/DV map in the water material class. We'll obviously initialize it in the constructor. Next, in the update uniforms method, we'll bind the DU/DV map in slot 2 and send it as a uniform. In the water fragment shader, we'll take in the new uniform. Next, we'll sample the DU/DV map with the 2D texture coordinates. Don't use the projected texture coordinates. We only care about the RG components, so I'll swizzle the vector. The RG components are between 0 and 1. We need the values between -1 and +1. So we'll multiply the components by 2 and subtract 1. We'll add this distortion both when we're sampling the reflection texture and the refraction texture.
So I added this DUDV map here, and I'm loading it in the water material here, texture load DUDVmap.png, and I'm sending it in the water material constructor. If we run now, we do get a distortion. However, it's absolutely exaggerated. Like, you can't even see the reflection and the refraction properly. It looks like a complete mess. You can easily solve this by going into the water shader and multiplying this distortion once again. This time by, let's say, 0.1. If we run now, yeah, it looks a bit better. There are some problems at the edges, but that will be something that we'll solve later. This is still quite a lot of distortion, however. I think I'm going to reduce it to even more. So I'll go to 0.02. Let's see what that looks like. Okay, that looks pretty good. Although that's a bit too little. Let me add a bit more. So let's say 0.4. Yeah, I think this is cool now. Look at that. What I don't like is that the waves are kind of really big. To make them smaller, what we can do is add a tiling factor. Let's go ahead and do that right now. So in the material, I'm going to add a glmvec2 tiling factor, which I'm going to default to 1. Sorry about that. And I'm going to set the tiling factor to the tiling factor. Now I'll send it as a uniform. So shader, set uniform. I'll have a U tiling factor, and I'll set it to tiling factor. In the water fragment shader, we'll add this tiling factor. And yeah, we'll add the uniform. Let's put it right here, or let's put it down here. Uniform vec2 U tiling factor. And right here we'll multiply by the vtex chord. There you go. Now if we run, we will get the same result. So let us add a new tiling factor. I'm not going to set it too big, I'm going to set it to just 4. Because if you make it really big, you start to see the pattern. So now, we'll get... yeah, there we go. I really like that actually, that looks pretty good. What doesn't look that good, apart from the edges, which we'll fix later, what doesn't look good is the fact that it's completely static. The reflection isn't, the distortion isn't moving. So let us add movement.
To make the ripples move, we'll add an offset variable in the water material. We'll initialize the offset to 0 in the constructor. Next, we'll send the value as a uniform. In the water fragment shader, we'll take in this uniform. Next, we'll add this offset to the distortion.
I'm going to do this part on screen, so I'm going to go in the scene header file. I'm going to add a float pointer. So I have this float x variable. I don't think we're using it anywhere. Yeah, in fact I'm going to change that x variable to be a float pointer, and it's going to point towards the water offset. In the scene source file, in the constructor, first we'll remove x, and wherever we're using it, yeah, here, we don't care about x. What I'm going to do is, first of all, this SD shared pointer, I'm going to change it to water material, and you'll see why. I'm going to grab this water offset variable and set it to the address of water material arrow offset. So now I have access to that offset. Now in the update method, we'll increase the water offset by delta, and we'll need to dereference it. We'll also then do water offset equal to f mod f of the water offset dereferenced and 1. This will prevent it from going to really high value, so it will loop back to 1. If we run now, we should get some effect. Let's see. And it's completely static. So I found out the issue. There wasn't a set uniform method that takes a float. This is very similar to the set uniform int, except it calls GL uniform 1f instead of GL uniform 1i. Now if we run, we have some movement, but it's absolutely ridiculous. It looks like there's some hurricane or something. So let's tone it down. I found out that by multiplying by 0.02f, I got a pretty decent result. Now if we run, well, that's a bit, it's good, I guess, but I'll increase it a bit more. I'll double it at least. So 0.04f. Yeah, that looks a little better. Let's make the distortion a bit more interesting. Let's add more distortions. So instead of just having distortion like this, I'll make a new variable. I'll call it distortion. I'll call this, the old distortion variable, distortion1. And I'll set distortion to distortion1 plus distortion2, which we still need to define. So distortion2 will be similar to this. However, I'm going to do something else. Instead of just adding the offset, I'll add the u offset for the x variable, and I'll make it go another way, the other way in the y direction. So minus, and I'll multiply it by 0.5 there. And you can add as many you want of these to add different currents of wind, sort of. So let's run and see what we get now. And yeah, there you go. Look, I don't know about you, but in my opinion that looks really nice. So yeah, there you go. There is one more thing I want to add, and that is, I don't want to hard code this wave strength here, this times 0.04. So I'll make it a uniform as well. Uniform float u, and I'm going to call it wave strength. And I'm going to use it in both places. In the water material, I'm going to add a float for the wave strength. I'm going to set it to, I'll hard code it, I'll default it to 0.04f, so we don't have to stay setting it. I'll add this variable eventually. I'll put it before the offset. I don't know why I'm doing that, but hey. and I'll set wave strength. We still need to define the wave strength. And we'll send it as a uniform. So shader set uniform u wave strength to wave strength. Sorry about that. There. Now if we run, we should get the exact same result. However, now we can tune it as we want. And there you go. Awesome. All is left now is specular lighting and some soft edges at the edge.
Let us start by calculating the specular lighting. In the fragment shader, we'll start by creating a new function called calcSpecularLight. This will take in 5 parameters. The first parameter is the light direction. The second parameter is the surface normal. The third parameter is the 2 camera vector. The last 2 parameters are the specular intensity and the specular power. The first thing we need to calculate is the light reflected on the surface. To get the specular vector, we use the dot product between the 2 camera vector and the reflected light direction. Now we need to scale the result with the specular power. We also need to multiply the result by the specular intensity. Finally, we'll return the result if it is greater than 0. Otherwise, we return 0. In the main function, we'll add the result of calcSpecularLight with the appropriate arguments. We need 3 more uniforms: the light direction, the specular intensity, and the specular power. In the water material class, we'll add the specular intensity and the specular power. In the constructor, I'll add 2 new parameters that initialize these fields. I'll default the specular intensity to 1 and the specular power to 8. Naturally, we'll initialize the fields. In the update uniforms method, we'll send the uniforms.
So if we run right now, we do get some shininess. However, there's not much detail. The lighting is behaving as if the surface is completely flat, which in reality it is. All it is a flat quad. How can we add detail to the water as if there are waves? You might remember that in a previous video we added normal mapping to these bricks, and that gave us detail even though the surface is flat. And the lighting behaves as if there are those, the grooves of the bricks. And that, my friends, is how we can achieve detail on the water. We can use a normal map. And that is what we're going to be doing. You probably can remember that when we did normal mapping, we needed the tangents. And we needed the tangents so that we can rotate the normals when our mesh rotates. Here's the thing, however, with water. Have you ever seen water that stays like this? No, right? It always stays horizontal, no matter where it is. So we don't care about the rotation. We can just use the normal map straight away, and we don't need to worry about the stupid Debian matrix and nothing of that sort, which is awesome. Let's go ahead and implement the normal map so that we get nice glistening waves.
Let's start by adding a texture for the normal map in the water material class. We'll take it in the constructor and initialize the field. In the update uniforms method, we'll bind the normal map to sampler slot 3. Next, we'll set the uNormal map uniform to 3. In the fragment shader, we'll add the uniform for the normal map. Right here, we'll sample the normal map color with the texture coordinates multiplied by the tiling factor and distorted. Also, we'll add the offset. Instead of hard-coding the surface normal to an up vector, we'll get the normal from the normal map color. The red channel is the x-axis, the blue channel is the y-axis, and the green channel is the z-axis. We need the x and z-axis in the range of -1 to 1, so I'll multiply both of them by 2 and subtract 1. Finally, we'll normalize the result.
Okay, so I did a couple of things. First of all, I added this normal map.png to the textures folder of our resources. And in the scene file, I loaded the normal map texture right here. If we run right now, we get an error because I've already tested this and we don't get the water. The error is I made a typo. Here this shouldn't be distortions, this should be distortion, singular, that's what I called it. Now if we run, look at that. We have specular lighting and the water is now glistening. That's awesome. All is left is to get nice soft edges because right now the edges look a bit weird. So yeah.
What we're trying to achieve is to get shallow parts of the water to look more transparent. So what we need is the distance between the water level and the bottom of the terrain. What we can easily get right now is the distance between the camera and the water surface. We do that by using the glfragchord.z variable. If you remember correctly, we are rendering the depth information under the water to a texture. So we can get the distance between the camera and the bottom of the water. With these two distances, we can finally get the distance between the water surface and the bottom of the water.
To get the distance between the camera and the water, we use a variable called glfragchord.z in the shader. For the depth value between the camera and the bottom of the water, we will use that depth buffer, that depth texture. There is a bit of a problem. Both of these depth values aren't linear. We need them to be linear, so we'll need to do a bit of a conversion. Let's go ahead and begin.
We'll start by adding the depth map to the water material. We'll add the parameter in the constructor and initialize it. In the updateUniforms method, we'll bind the texture and send it as a uniform. In the fragment shader, to calculate the floor distance and the water distance, we need the near and far clipping plane value. I'm going to be lazy and hardcode the near and far clipping planes. These values should be the same values you put in when creating the perspective projection matrix. We'll grab the depth value from the depth map. To get the linear distance, we'll perform this calculation. We'll do the exact same calculation for the water distance. All we have to do to get the water depth is to subtract the floor distance from the water distance. All we need to do now is set the alpha component of the output color to the water depth. However, I'll divide this by 5 and clamp it between 0 and 1.
I almost forgot to add the depth map in the shader, so that's important. In the scene source file, we now need to pass in that depth map into the water material. And to get the depth map, we just grab the refraction frame and get the depth attachment. If we run now, it actually won't work, you'll see. There, you see, it's exactly like before. The edges are not soft at all. So we set the alpha, right, in the shader. We set the alpha to the water depth division by 5 and we clamped it. Why isn't this working? Why is it still opaque? And the reason for this is that by default OpenGL doesn't blend the alpha channel, so it doesn't do alpha blending. To enable it, it's very easy. We first enable blending, and then we set the blend function. We can set multiple types of blend functions. We want GL source alpha and GL1 minus source alpha. And it's not coming up in IntelliSense. There we are. And this will do proper alpha blending. At the end, I'll disable blending, just so that if we add something else in the future, it won't cause problems. Now if we run, There you go, look at that, we have soft edges. That's awesome, it looks so much better. There is one last thing, as you can see at the edges there are kind of pixels there. This is actually pretty easy to solve. In the clipping plane, when we're rendering with the clipping plane here, we'll add a tiny offset here. Let's try 0.5f. So we set the distance to an offset of 0.5f. And we still don't see any, we still see pixels at the edge. Let's try maybe 1. It still appears a little bit. I experimented a bit off screen and this is the best one that I found. So on the bottom clipping plane I just added 0.1f as an offset. And now if we run, there you go, no more problems with pixels poking out. Awesome. And that, my friends, is the end of this video. Water is done. It's awesome, isn't it? Now there's one final thing we need to tackle. In the next video we're going to start tackling shadow mapping. Yes, we're going to get shadows in the next video, or at least we'll start working on getting shadows. So if you want to be notified when the next video is coming out, please consider subscribing to the channel and hitting the notification bell. With that, thanks a lot for watching and goodbye.